All right, in this video, I want to take a moment to discuss the concept of desolvation. Desolvation. And its effect on the pKa of protonatable molecules. And the reason I'm bringing this up is that, as you will see, this is an important concept for part of the journal article that you're reading. So to understand this, we have to look at a protonatable molecule. So let's take a look at a carboxyl group. So we have C double bonded to an O, and it's in its deprotonated state, and we have a proton over here. And we know that pKa is a measure of the affinity for this oxygen to this proton. Right? The higher the pKa is, the more likely that proton is going to be covalently bound here to that oxygen. The lower the pKa is, the more likely that this carboxyl group is going to be deprotonated. Okay, so that measures that affinity. Now, remember that that this molecule that we're looking at is going to be part of a protein. Okay, that's what we're studying. We're studying the synthesis of this enzyme that the scientists are making. And remember that this protein doesn't operate in a dry environment. It's dissolved in an aqueous environment, which means we have water molecules. Water molecules. Water molecules, water molecules, water molecules, water molecules, right? So really what we're seeing here is it is solvated, right? I'm not sure if that's an actual word, but it describes what we have here. But we still have our interaction between this oxygen here and that hydrogen, right? They can covalently bond if we increase the hydrogen ion concentration enough. So what desolvation is now is just the opposite of solvation. It is removing some of those water molecules. So to understand what effect that has on pKa, let's just understand what effect the water molecules have on it before we look at the effect that taking them away does to it. So when we have these water molecules here, what's pretty obvious is that they are interrupting the possible interactions between this H plus and this O minus. Right? Sort of impeding them the ability of that covalent bond to reform. Now, it's not completely stopping that ability, it's just hindering it a little bit. And if we have defined pKa as the affinity of the oxygen here to this hydrogen, then if we are hindering that ability, then what we are doing is that water molecule is lowering the pKa, lowering the ability of that oxygen and that hydrogen to covalent bond. Which means if we desolvate, right, and that's the important thing, is that scientists have such control over the microenvironment of the active site of the enzyme that they are building, they can do things such that they are desolvating or removing water molecules from the active site of that enzyme. And when you do that, when you desolvate, you remove those hindrances that are keeping that O minus and H plus from interacting. And so what desolvating does is it increases the pKa of this carboxyl group. Okay? It increases its basicity, meaning that it now has a higher affinity for that proton to become OH with no charge. Okay. So now go back to the journal article, read the portion that talks about desolvation, and see if that makes sense.